Good morning, students. Welcome back. In the last class, we started our discussion with the normalization, and there we come to know about first and second normal forms. Today, we are going to learn about relational DBMS part 4, and we'll be discussing about transitivity property, 3NF means third normal form and its example, trivial dependency properties, BCNF means Boyce Codd normal forms and its example, decomposing a schema into BCNF and comparison between 3NF and BCNF and the difference. So let's start with the property called transitivity property. Transitivity means it is not directly. There is some transit through which we are determining someone else. So here we are taking a relation R where there is 4 attributes. You can see in the screen A, B attributes are underlined. They are called as candidate key, and C and D, these 2 attributes are non-key attributes. They are not taking part in the formation of a primary key. Here in the first dependency, basically AB, the whole key is determining one of the non-key attribute, that is C, and C again determines another non-key attribute, that is D. So this is what the transitivity property is. That means AB is the whole key that determines D, but that is via transit. The transit is what? Another non-key attribute, that is C. So here the observations are C is a non-key attribute that becomes a determinant, and that is how is helping AB to determine D. That is also a non-key attribute. Okay. Now D is determined directly by C and indirectly by AB via the transit C. Okay. So already we have discussed AB primary key and it determines C, and AB transitively determines D. Now we will detail what 3NF or third normal form is. Third normal form in database relation after 2NF, the programmer or database administrator, they try to convert the database into 3NF compatible one. And if we need to make a relation 3NF compatible, then we have to take care that it is already in 2NF or not. It must be in 2NF and no non-key attribute will be transitively dependent on the primary key. What it means? That means there is no transitive dependency basically. And also it should satisfy one of the below given conditions. So the condition is that if there is a function dependency C determines D, C should be a super key and D should be a prime attribute, that is D should be a part of the candidate key. So any determinant cannot determine any other attribute which is out of the super key. That means it also confirms that any determinant cannot be a non-key attribute, that must be within the part of the super key, right? So this is the conditions that 3NF follows. There should be no transitive dependency as well as these two conditions are also being followed. If we are clear with that, then we need to know where or in what type of application we say that it is 3NF compatible. 3NF is used to reduce data duplication and to attain integrity. So, to attain integrity and reducing the data duplication, 3NF is used. Now, let's give an example of 3NF that should be in a super key and the determinant should not be a non-key attribute. So, to exemplify that, let's discuss about this particular example. Let's say we have a relation R where there are 5 attributes L, M, N, O, P. And what are the functional dependencies that we are having? That F is the functional dependency set. Here L determines M, Mn determines P, and Po determines L. Now in the left hand side, look at this: L, then Mn, then Op. So whatever is there, all the attributes, if we combine them together, that means they are all is the part of the super key. So super key is the combination of all determinants. So here L, Mn, Po, all these attributes which are basically are present in the relation R, they are actually the super key sub parts. Now if we find out the candidate keys in this relation, then we will see that LNO can determine the other attributes, MNO can also determine all the attributes, NOP can also determine all the other attributes. So these three can be called as, so these are the minimal subset of the super key that can also uniquely identify a tuple in this relation R. That is how all these three set of keys are called as candidate keys, and they can define all 5 attributes present in relation R. And this relation is in 3NF as it is already in 2NF and has no transitive dependency. Also, there is no non-prime attribute that is deriving a non-prime attribute. So there is nothing which can be causing that the relation must not be in 3NF. So there is no anomaly like that. So there is no problem to say that this relation R is in 3NF. If there was any, let's say, transitive dependency, then we could oppose that it is not in 3NF, but that is not present. That means the transitive dependency is not there. As well as in the previous slide, we come to know that if anything is a determinant, that must be a super key, and which is being determined must also be a part of the candidate key. So here we can see that LMNOP, all these are under the super key because L is the determinant first, Mn second, and Po. So if we combine them all together, all of them are the subset of the super key. And whichever being determined, M, P, L, all are the part of a candidate key. So here we have L, here we have M in the candidate key list, and as well as P. So all these attributes are a part of the candidate key. So all the two prerequisite that is important for satisfying a relation as 3NF, so that those are holding. So this example says that this relation R, whatever functional dependencies it has, are in 3NF. Now we need to know the Boyce-Codd normal form. So immediately after we come to know about this 3NF, we need to understand what BCNF is, right? So BCNF stands for Boyce-Codd normal form that all of us know. But this Boyce chord normal form, it is uh, this name is given from two scientists' name. One is R.F. Boyce, another is E.F. Chord. And in 1947, it was given, and BCNF is an advanced version of 3NF. That is why it is called that it is stricter than 3NF. And a table is in BCNF if every functional dependency, let's say x determines y, x is the super key of the table, and for BCNF the table should be in 3NF. It must satisfy that it is in 3NF, and for every functional dependency LHS is a super key. So let's clarify it. A relation schema R, let's say this is the relation schema, it can be called that it is in BCNF with respect to a set of functional dependency F, where for all functional dependencies F plus, that is the closure of the form, alpha determines beta, let's say, where alpha is a subset of relation R and beta is also a subset of relation R. Now after this, at least one of the following should hold. What is that? Alpha determines beta is a trivial, that means beta is a subset of alpha, or alpha is a super key for R. Okay, so this is what the Boyd normal form. When we will give example, then we should be more clear about it. Okay, so let's take an example from here. Now in BCNF understanding, this is one of the most confusing and difficult concept in DBMS, but let's make it simple. Okay, so the first thing that I would like to tell you that there should not have any trivial dependency. This is the first thing, that there should not be any trivial dependency, and the second thing is that non-key attribute cannot be a determinant. So if in the table there is a non-key attribute, so let's give an example here. Look at this uh, particular attribute, which is C. It is a determinant of a particular partial key, that is B here. Now in the above figure, in this, C is a non-key attribute and is a determinant as well, and it violates BCNF rule, though it is in 3NF. Why we say that it is in 3NF? Because there is no transitivity thing here, because non-key attribute is not determinant of a non-key attribute in turn. So that is why it is not violating 3NF, but it is not yet in BCNF. So let's decompose this relation and let's understand how we can convert violating BCNF relation into BCNF1. So let R be a schema that is not in BCNF, and let alpha is determining beta be the functional dependency that causes a violation of BCNF, right? Now we decompose R into alpha union beta, and if we subtract beta minus alpha from relation R, so let's give an example here, otherwise it will be little confusing to you. Now here if you see this particular example in the last slide, that there was this one, AB determines C and D and C determines B. So what exactly we need to do is C determines B. This is the place which is creating problem, that means which is causing the violation of BCNF, right? So what we do, we take R1, that is the decomposed relation, first decomposed relation R1, that combines this C and B two attributes. So R1 contains C union B. These are the two attributes that first decomposed relation contains, and the second relation should have A, C and D. How we get it? R minus B minus C. So we exclude B from relation R we will only have A, C and D. So this is the second relation that we are having, and this is the first relation. So after decomposition, we can say that it is not violating BCNF because there is no trivial dependency. Any non-key attribute is not a determinant now. So that is why it is not violating BCNF. So the two relation R1 and R2, here it is R1 which comprising of two attributes C and B, and R2 is another relation, decomposed relation, which contains three attributes and they are A, C and D. So this is as simple as this, and these two relations does not contain any non-key attribute to be a determinant. So there is no trivial dependencies present in this two decomposed relation. And definitely if we combine them together, that means if we join them, then we will get the relation R. Okay. So this is what, and BCNF is the example of BCNF. Now let's compare between BCNF and 3NF. What lies in BCNF and 3NF? Advantage to 3NF over BCNF, let's discuss. It is always possible to obtain a 3NF design without sacrificing losslessness or dependency preservation. So without sacrificing the losslessness or dependency preservation, we can achieve 3NF. So 3NF achieving is easy because there should be no transitive dependency, and all the determined must be present in the candidate key list, and also any determinant must be present in the super key list. So that is how the 3NF is easy to understand and easy to achieve. But there is some disadvantage of 3NF as well. So we may have to use null values to represent some of the possible meaningful relationships among data items, because when we to make all the attribute which are being determined, if we have to include them as candidate key, then sometimes we need to put some field values as null, and that leads to a problem because handling null is not possible always by different SQL functions. So that is why in 3NF we may have to use null values to represent some of the possible meaningful relationships. And there is the problem of repetition of information, right? Now, in this particular slide, we will tell you about the difference between 3NF and BCNF, and this is very, very important from the perspective of exam and understanding as well. So let's talk you about the 3NF first. 3NF is the third normal form, and there should be no transitive dependency, the first point, key point, and that is no non-prime attribute should be transitively dependent on the candidate key. Whereas the BCNF, for any relation, let's say A determines B, A should be a super key of a relation, right? So this is the first thing that we need to know, that any determinant that must be in the super key set. Okay. Now in the second point, 3NF it is less stronger than BCNF, and BCNF is comparatively more stronger or stricter. So third point, in 3NF the functional dependencies are already in 1NF and 2NF, already in 1NF and 2NF. And in case of BCNF, the functional dependencies should be 1NF, 2NF and 3NF compatible first. The redundancy is high in 3NF because we sometimes may have to put null values to uh, manage the determinant to be in the list of candidate keys. determined must be present in the candidate keys. So to achieve that, we sometimes have to uh, suffer from redundancy. But in BCNF, the redundancy is comparatively low in this particular Boyce Codd normal form. And 3NF, there is a preservation of all functional dependencies. So functional dependencies are preserved, whereas BCNF, in BCNF there may or may not be preservation of all functional dependencies, because sometimes what happens when we try to accomplish BCNF, then it again violates the full functional dependency, and we have to rethink about that and have to make that 2NF compatible again. So that is why it is said that it is stricter, very, very stricter than 3NF and hard to achieve. Point number 6, it is comparatively easier to achieve and it is difficult to achieve. Again, stronger, this and this are looks little bit similar. The last point is lossless decomposition can be achieved by 3NF, and lossless decomposition is hard to achieve because we have to uh, divide the tables to make it BCNF compatible, and sometimes it is not possible to uh, make it lossless decomposition. Okay, so these are the 7 differences between 3NF and BCNF, but there are few similarities like point number 2 and 6, they are almost same in understanding. Anyway, so this is the 3NF and BCNF comparative study. So I believe that you understood the concept of 3NF and BCNF. So let's meet in the next class where we'll be discussing about 4NF and 5NF and some other terms like DKNF and TJNF. So thank you till then.